SAP 2000 as well. So many features will be common as far as the graphical user interface is concerned, right? Now, ETABS is focused on a design office requirement where you need to generate a lot of drawings and details, structural drawings and details day in, day out. So it is focused on the design office requirement and many features related to that, such as automated features that you can see easily available in ETABS. But SAP 2000 is a general purpose structural analysis program where you can model any type of structural engineering problem in the SAP, perform analysis and perform design of members as well. So the program is more focused on the analysis. So you'll see a lot of analysis features in addition to what you have seen in ETABS. So those are the examples for my today's presentation. Just to give you slightly on the modeling part, we'll take up one small example, a similar example we saw in ETABS, and then we'll quickly switch to other examples. This is to give you an introduction to all the features and how we use it. And there will be some differences compared to ETABS, and that also we will see in this particular example, right? So this is the interface you get, and typically file menu, through which you create a new model or open existing models. You have import export options for various other formats, and then print, report, and recently opened models. Let's start with the new model. I'm taking up the same example so that you will connect easily with the previous example and can quickly cover the features as well. So it will show the first form, which is called model initialization. So it is to set the unit system in which you're going to work with. So I'm setting kilonewton meters. You have other options like pounds and inches, tons and meters, etc. So one thing in both the programs about the unit system is it is dynamic. That means at any point of time you can change the unit system even after the analysis or even design. In the desired unit system, we can get the values. So it will be much convenient in some situations, but for this example, I'm going to set it to kilonewton meters, and then the default materials you can set to a specific region. This form also allows you to bring in settings from an existing model file. If you have similar model, some complex definitions that you have made, it is not required to create, define each and every definitions again and again for every new model. You can bring in the settings from an existing model. That's the second option. And then you have templates, and the templates shows what are the types of structures, starting from a simple beam, 2D plus 3D plus 2D frame, 3D frames, walls, flat slab, shells, and other storage structures, underground, solids, and pipes and plates. So many structural templates are available readily. You can quickly start with. But typically, we would like to have a good control over the model, whatever you build, through a grid system. So we go with grid only option and specify the data. It is a Cartesian or a rectangular grid system. And then you have a cylindrical as well for circular shape structures. Let's go with the Cartesian. Let's have 4, 4. So number of grid lines X, Y, Z. So here, unlike ETABS, you'll have The grid system defined simply based on the x, y, and z axis. In ETABS, you had x and y, and then in z, along the z direction, you had stories. Number of stack of stories you can call like 10-story building, a 50-story building. So you have story idealization in ETABS. Here we have no such idealization. It is purely based on the grid lines, based on the coordinates, global coordinate system. So global coordinates are x, y, z, and then there are local coordinate system for the members, starting from a joint line area. Those are labeled as 1, 2, 3. Both will follow right hand rule. You open first three fingers of your right hand. Thumb is X, index is Y, middle finger is Z. So Z by default Z is along the height of the building. So when you look at the building in a plan view or the structure in a plan view, then you'll get to see X and Y, and Z will be along the height of the structure. So X 4, 4 means you get 3 spans. Again in Y direction 4, 3 spans, and Z direction 5, that means 4 stories. And then the spacing, you can specify it as uniform spacing here. Later you can modify this under the definition. Just for a quick start, let us have these default values and then the origin 0, 0, 0. And with that, if we press OK, a grid system will be generated. Note this is just a grid system, no members are present. We are going to model them shortly. So ETABS and SAP2000 both are finite element analysis programs. However, we are dealing with object level, not at the finite element. If you want, you can take control and do the meshing, discretization of the object into desired number of elements, and those control is always there. But you don't have to worry in most cases, especially in ETABS. But in SAP, you will have to specify a certain meshing setting to the objects. So that's where SAP is different from ETABS. We will see those. So in ETABS, there are default settings assigned to each object that you model. For example, a beam, a column, a brace, and even shell, walls, etc. But here, specifically for shells, you will have to deal with the mesh setting every time when you model a new object, shell object, or use a shell object structure. All right, let's quickly look at the interface. You'll get Model Explorer, through which you can access to various property definitions, load definitions, etc. As a quick access tool, a feature, you can click and drag and drop it on an element to apply some kind of fancy GUI things that you get. But as a new user, I would suggest not to use this, but focus on the menu item. Right. Even the shortcut icons on the left, these are grouped vertically for the on the left pane. It is for the select, draw, and snap for quick access. You'll get used to these as you uh, practice, and after a couple of models, you know where the shortcuts are available. And on the top, you have the file save related, and then quick analysis shortcut, and then you have zoom, view, display options, and after analysis and design, you have the interaction for those outputs. So these would be the shortcuts, and typically you'll be using a lot. But as a present for the presentation and as also for the in point of view that you're getting trained here, you need to use the menu items. I would suggest for both ETABS and for SAP, you can look at the menu items and look for the command you're searching for. So in both, the menu array items are arranged exactly in the same way. So leaving the file menu first, And then the edit and view, it's edit to edit objects, as you know, and view is to set views. After that, you start with the define. So define definition of materials, section properties, right? Load patterns, load cases, load combinations, all the definitions required for your structure that is to be modeled are defined first. This is because we are dealing with object-based modeling. When you say an object, for example, a beam, it has a material property. It will also have the section property, like the sectional dimensions. So you'll define such an object and use them directly to model the structure, structural members. So that's why we need the define or the definitions as the first step in your modeling. Once items are defined, then we'll use them to draw the structural members or model creation. Once you have drawn, you can select the members and assign them. These two menu items will be used combinedly to complete your various assignments such as properties, change of properties, assignment of loads, for example, wall loads or floor loads, live loads, dead loads, etc. We'll assign them and complete your assignments. With that, your model will be ready for the analysis, and then you'll perform the analysis. That's the analysis menu. And then you have the display of analysis results like support reactions, member forces, shell stresses, etc. under the display. And then you review the analysis outputs, various responses. If you're convinced, you can perform the design of the members, such as steel frame design, concrete frame design. These are the two primary design feature that you'll be using in this. And then you have concrete shell design, which is based on Eurocode. And then you have aluminum and cold form, other additional design modules, right? ETABS will have sophisticated design tools such as slab design, shear wall design, etc. But this is more focused on the analysis. So we have standard steel and concrete frame design modules. All right. Our focus would be mostly on the analysis part and the modeling part. All right. So that's the interface and the various commands and tools that are available in that logic, and exactly how the menu is arranged. You can see this is same for ETABS as well as SAP, starting from the define and ends at the design. Right. In that logic, you can find the tool you're looking for. Let me save this once. Call this one, building one, and then file type is .sdb. ETABS is EDB. This is SDB. Let me save this. Right. You'll be dealing with planes. You can see the shortcuts here: 3D, X is at Y is at, and then XY planes. Right. You'll have currently this is an XY plane, and on the right side 3D view, it is highlighting in cyan color which level we are currently in. There are big arrows. You can also use this to quickly go up and down in that particular plan or elevation. All right. We close this model explorer, which I will not use. And on the left bottom, you have the information bar. Depending on the activity going on the working window, you'll get some information. And then on the right side, right bottom, you can see the mouse coordinates X, Y, Z. Then the viewport, and then the unit system, which you can change at any point of time. All right. Let's quickly go through the definitions and then the modeling. We'll start with the material. The forms may be slightly different, but for the presentation sake, I'm going to take you through logically it will be the same as what you had seen in ETABS. So under defined materials, you have these two, and then you have add new material. You can quickly create material based on region. Let's say M25, that will be added to the list. If you want to modify, you can select the material and then press modify show material. This will take you to the actual material property data. You can see here. Locally, you can also change the units, and you can see the the mechanical properties for concrete material. Since you'd be using this for advanced analysis, there is an option to switch to advanced properties. So the previous form was showing all the uh, linear properties for linear static analysis. And when you're into nonlinear analysis, such as nonlinear static, pushover analysis, or time history analysis, dynamic, then you need material nonlinearity as well as geometric nonlinearity. So this is material nonlinearity. You can go here and see various definitions that you can make here. So material can be temperature dependent. If you go to modify, show material properties, and the bottom you can find advanced material property data. For example, this is concrete, uniaxial nonlinear data. It uses a strain curve of Mander concrete model as a default. You can also convert it into user defined and modify the way you want. So if you look at this strain plot, you can see this. You can also specify that is confined or unconfined with other details for the desired use. You can also specify the time dependent properties like shrinkage and creep based on standard guidelines and codes, or define on your own. For now, I'm accepting the default. So I'll uncheck this advanced properties. And I will add one more material, which would be a rebar material. Let's say F500. Add this. All right, let's hit the save button once. And then let's quickly define section properties. Quickly define a frame, a beam, a column, and a floor slab. Frame section. So there will not be any predefined list of sections or properties. You'll have to add new property here. Import new properties for structural steel. Standard sections you can import from the library. So this one is concrete, and I'm going to change the type to concrete, and you'll get sections. Let's go with the rectangular. Let's call it beam. I'm naming it as B250 450. And then the material, let's use M25. And this is sufficient for the analysis, but we are interested in the design. Then you can set the concrete reinforcement information, basically to tell the program which design type to be used. By default, it will be concrete. I'm switching it to beam, rebar material, and then the effective cover. That's what we need to specify here for the design. Using 60 mm for both top and bottom, assuming 2 layers of steel. I'm accepting this. And you can see the plot has updated now without any rebar shown inside the section. This is a beam type design. For columns, there will be rebar layout. Next, what we will design after this. But importantly, look at the local axis shown here, 2 and 3. This is important. You need to know the local axis of each element type. Work with the SAP because you need to rotate or orient in certain angle as per your model needs. So local axis for a line, whether it's a beam, brace, or a column, the local axis one runs along the length of the line element. 2 and 3 will be on the sectional sides. That's what you're looking at, 2 and 3. So imagine this is a beam section, and 2 will be carrying the shear. The shear distribution can be found in 1-2 plane, and then in the same 1-2 plane, you will see the major moment where loads are acting on top of this section, like from here, and then rotations or the bending moment will be about local 3. Then you will see major moments about local 3 axis. So this you should know. Sufficient for the beam. Next, we'll go with the column. Let's go 300 by, okay, sorry. You'll have to add new property in that. Let's go with rectangular. 300 by 500. It's called depth 0.5, 0.3. Let's use M25 concrete reinforcement. And here we will specify the design type as column, rebar FE500, and clear cover, and these information to update this. So in local 3, I can increase, sorry, local 2, I can increase number of bars. Let's put 5. And then you can also specify the size. And the column will be designed. That means it will give what is the ASC required after the design. You can also tell the program to check for capacity for the provided reinforcement here. It will give you demand capacity ratio. If it is less than 1, then it is safe. Greater than 1, it is safe. So you have both options. So you can see the refined layout, be more realistic. So this is important because the program needs this information for generating PMM interaction surface for the design. So program does not use the SP16 charts. It generates a 3D PMM interaction surface for each column that you define. It will be more realistic, and it can also define other shapes. There is an option called under the other section designer. Of any shape, arbitrary shape, such as a cruciform, H, Z, or any shape. You have various, there's a graph sheet available for that in which you will be drawing the section. You can use any shape, standard shapes are already available. You can use, or you can even use any. This is not part of the presentation, but I want you to know how these sections can be defined. You see, easily you can define this. And there will be a section, and as any other section you can use. in your modeling. We'll delete this. We'll deal with only the rectangular sections, but you should know it's useful to define composite sections also. The last one is area section. So you can also see other types of properties, section properties you can define, like such as tendon, cable, area, solids, and we also have link and then hinge assignments. Links can be used to define um, highly nonlinear devices such as dampers, isolators. We will see one example on that. So we have the link for nonlinear force deformation behavior that can be defined and used. So link element also present, and then frequency based link properties, and then hinge properties. This, for example, you're doing a pushover analysis. You want to study the nonlinear uh, response of a hinge, like a moment plastic rotation of frames. You can use the hinge properties for that. We have that option as well. So we have all the necessary elements that can be defined for any structural engineering problem in this. Right. Let's complete this with the area section. It's a shell. You can also have planes and also axisymmetric solids. Let's use shell. The common name is shell, and then you add a new section. And here you have the types: the shell, plate, or membrane. Shell will have both in plane and out of plane stiffnesses. Plate will have only out of plane. Membrane will have only in plane. There is one more option called layered shell or sandwich shell for nonlinear analysis for studying a sandwich section such as confined concrete, unconfined concrete, rebar, steel layers, and their responses in a sandwich shell for a nonlinear analysis. So we have all the types here. In this case, we'll use a membrane. We use membrane that is having only in-plane stiffness, which is sufficient for most building type structures. And our interest is to only transfer the loads applied to the floors to the supporting beams on the edges. So out of plane bending of the slab is not relevant for this analysis. The superstructure is a bare frame of concrete and beam. So that can be other types of structures such as flat slab where you need the out of plane bending of slabs. Then you can use shell thin in that case. You want to model uh, the base or the raft or the foundation system. So in the previous example, we saw we assigned the fixed base to the columns, right? Pin type or fixed type. So those are idealized support conditions, but we can also model footing, combined footing or a raft, and assign them with soil springs or the area springs to study the soil structure interaction. In that case, you can use shell thick. It can also be used in those situations as well. It depends on the forces, other forces acting on the or expected response in plane or only out of plane. You can choose from them. So membrane is a simplified one, has only in plane, sufficient for most building systems with that has beam slab system. Floors are resting on beams. All right. Here I'm going to specify a thickness of 150 mm for both membrane and bending. Out of plane, membrane is in plane. Then material M25 can use. So that's all we need. Let's name it, yes, 150, just to identify it easily from the name. So you don't have to open the property and see what is the definition. If you enable it as S1, S2, S3, it's going to be difficult. If you name it with thickness, it will be easier with some more information. All right. So we have S150. That's the section property definition. And then we jump to the load pattern. The default a dead load pattern, name dead, and type. You can see various other type that are possible. Dead, live, wind, seismic, notional, pattern live, temperature, snow, sea state, pre-stress, right? Various other types are also available. Now we use the same dead load pattern, and we also define one more called live for assigning live loads. So load patterns generally are to break up the various loads acting on the structure in various patterns. So dead and live are gravity loads acting downwards on the structure. Then there are lateral loads like seismic and wind laterally in x and y direction. Right. So we have various patterns. So we call it as load patterns. And this also helps the program in two ways. One is to create load cases for the analysis. So whenever you define a load pattern, program automatically creates a load case in the same name so that uh, the results are available for that load pattern as a load case result. We had seen this in the ETABS as well. We quickly add live. Let's give only two. Similarly, for the lateral loads, you can also define. I'm skipping the lateral loads here. We'll go for advanced analysis like response spectrum definition. So we'll not deal with the linear static anymore, except for the dead and live. So here also you can define earthquake, type, seismic, and define a lateral load definition using auto lateral load pattern. So I'm skipping that part. Let's keep dead and live. And one more thing is the self-weight multiplier with the dead one, which is default. So whatever you draw, you forget about the self-weight. So program will capture that self-weight and add it to the dead load case. So it is always uh, convenient to do that way. So if you don't want, you can put 0 here. Modify this as 0. Self-weight will be ignored. That's how it works. All right. And as I said, if you switch to load cases, you can see dead, and then there is a live. And model is also a default case. It's defined. If you don't want, you can delete this. Let us have this model for now. And load combinations. So we can generate our own combination or add default load combination based on the selected code. We'll come back to this later. Our focus will be on the modeling and the analysis. Let me quickly, you cannot draw directly the columns on the plan view. So you'll have to switch to an elevation view. So we'll go to the view. You can also use the shortcuts, but I wanted to show you where it is. Elevation view, set 2D view. And here I can set the x is at plane and y equal to 0. This is the origin 0, 0, 6, 12, 18 in y direction, same in x direction. So I'll use x is a plane, y equal to 0. That means this elevation. Press apply. You can see the cyan color on the 3D view. And if you use up or down arrow, it will switch to next one. Right. For drawing columns, here you will have to switch to an elevation. In ETABS, you can directly draw on a plan view. That's one small difference. Again, under the draw, you can find similar drawing tools or commands. You have the default cursor, which is set select mode. And then when you're in drawing mode, you have these options: a dot, or I mean a joint, line, and then area. and then you also have the link. So these are the various types to deal with to create your structure. Now, joints, you did not create any joints um, unless there is a special requirement. So when you draw a line, program can recognize from its ends there are two joints. So program can identify the joints as you model. For example, if you draw a rectangle area, the four corners joints are identified, and when it gets meshed, the meshed locations will have joints, and program will recognize internal joints automatically. So you don't need to worry about the joints. You can quickly draw the objects. Let's say the columns first. So I'll go for draw frame. Since we are having a grid system, we can make use of the quick draw options. So quick draw frame. I'll select the concrete column, and then you can click easily. So the idea is to complete one story um, at the bottommost level and then replicate it in other levels easily. I can come out of the drawing mode by pressing escape key or draw set select mode and select these columns. You can see in a 3D view. From here, I'm going to replicate in these grids. So it's called replicate. This is available under the edit, replicate, a linear replication. So you know in y direction it is 6, number 3 times, and apply. Now we can switch back to XY plane. I want to go to the lowest level, not at the base, just above that. And here I can quickly draw the beams. Make a selection window or click on the grid lines, it will create objects. Quickly next we draw quick draw area object S150, then select mode. Let us select the slabs and assign them. You can use various selection options using this menu. Set of selection and set of deselection are available to arrive at the final set of selections you want. You can use property based selection or labels, whichever way is relevant for that. So you need these various options when you're dealing with a complex model, especially. Right now, the model is very simple. I'm using my mouse as a selection tool easily. And now I'm going to assign area loads. Under area load, there are various options. You can see specifically in this, I want to transfer the floor loads to the frames, I mean the beams. So uniform to frame shell. So for the dead, sulfate is already taken care. So we are going to apply the additional loads such as floor finish. So the application is in gravity, and then we as a two-way distribution. Let's give 1 kilonewton per meter square and replace existing load is fine and apply it. Note in this selection, it also selects the frames or the beams. And when I'm applying the area load, it goes only to the area load. So frames are not get affected or not loaded with this assignment. This time live load, gravity two-way, let's say 2.5 kilonewton per meter square, and replace existing load. Replace existing replaces anything in the live. It is not relevant to the dead load pattern. Any changes will happen only to the selected pattern. So it's okay, and you can close. And right click. You right click, it will bring the object related information starting from the location, coordinates, assignments, lab property, and then loads. You can see dead load 1 kilonewton, live load 2.5 kilonewton, and two-way distribution. You can also assign frame loads. Let's say only the periphery, and you can go to the assign after selection of the periphery beams and frame loads. You have again various options: point load, distributed, temperature, strain, and deformation. You can see we will use distributed load UDL. We'll consider the brickwork or the masonry load under the dead with gravity force. You can also switch to moment to apply moments or torsion as the force and uniform load of let's say 10 kilonewton per meter. And there is a trapezoidal load to apply trapezoidal load such as uniformly varying load or varying. I mean loads are applied only partially on the beam. You can use the trapezoidal load. And 4 control points are available. Using that, you can complete your assignment. So this is UDL. So we'll use uniform and apply it. Close this. Right. Now let's replicate this in other levels as well. So I'm going to select all. I'll go to edit, replicate. So vertically, so x is that equal to 3 and 1, 2, 3. 3 levels with number of times 3. And this will replicate everything, including the property, load assignments, etc. And the last assignment would be the support conditions. Unlike ETABS, here support conditions are not automatically assigned, so you'll have to assign, else program will throw errors. Let us select base joints assigned. You can use various options out there. Let's use coordinate specification and click joint in XY plane. It's an XY plane and there is a joint. You can select and that will select 16 points. Now you can see the left bottom, it shows number of objects selected, 16 points selected. And to that, you'll assign joint restraints and you can assign a fixed, or you can also individually control this. To remove, you need to use the last one or uncheck all the restraint directions. Let's use fixed and apply. That's how we um, model this structure. Let me use one more load case type, response spectrum case. I'll quickly go for the definitions. First, we'll need the mass source. You have the mass source. We'll modify the existing one with specified mass pattern. Dead load 100%, live load 25%, which is 0.25. This will be the mass source. I think the same we did in ETABS as well. This is the same mass source for your seismic. load cases. Now, under the load case, we have a model load case which is required for studying the dynamic characteristics of this building, such as time periods, frequencies, and also the model mass participation ratios, etc. So this is required because we are going to use this model results for your response spectrum analysis. So let us quickly see what's inside this. It's a model type, and you can set the type here. So various other types you can see here. It's a model eigenvectors. You have Ritz vector as well. Let's go with the eigen. Number of modes will start with 12 T per story. So we have 4 stories, so 12 should be sufficient. And then you have additional controls to do this. This model definition should be fine. And let's add a new case. Okay, I will come back to this. Before this, let's press OK. So we are going to define response spectrum case. And for the response spectrum case, we need to define the functions first. Response spectrum function, which is again under the define functions. And here you can see response spectrum, time history, power spectral density functions, and steady state functions you can define. Well, the last two are for frequency domain analysis. The first one we are going to use to define the response spectrum. So here program has various code based spectrums ready for use. We're going to select, let's say, Indian code IS1893 and add new function. Same it as IS1893. And then we have, let's select zone 3. Another parameters. So the function you can see here. Program also gives you option to generate synthetic or generated earthquake also get it from there. But let's stick to the Indian and we'll proceed with this. Let's go to the load case. Add new load case. Let's call it as spec X. And the type it is going to be response spectrum. We can see I'm changing the type, and the form will also alter. The model combination type and directional combination type is specified here, and typically we'll be specifying the acceleration spectrum, which is defined here. So U1 is the joint local axis. U1 is by default oriented in X, global X. So we're going to apply this in X direction. So you can use U1, and function is IS1893. Scale factor is 9.81. And add this. So this is the load. And for model damping, it is using 0.05. Constant damping for all modes. So we define one more, or just make a copy of this existing and change this to spec Y. So the only change we'll make here is the direction U2, which is Y direction, U3 is Z direction. Translation in X, Y, and Z, and then rotation about the respective axis. So this is only U2, and that's how you define the response spectrum. Now we are going to run this analysis. Under the analyze, run analysis. Analysis is complete. Now under the display, you can see show deep form shape. So it is currently showing the dead. So first case, then you can switch to, we skip the dead and live. We have already seen this in ETABS. I'm going to the model, and for the mode 1, we are going to see, you can see the mode shape. You can also set the animation, set translation, mode 2, there is a torsional mode, mode 3, this is translation in X direction. So ideally torsional mode should not be in 1 and 2. So we'll have to work with the stiffness, or introducing shear walls will also help in avoiding those torsional modes. But for demonstration's sake, we'll continue without any modifications needed for this model. Importantly, what we also look at in the output is through the show tables for the model results. You will see under the analysis results structural output, model information. You will select model periods and frequencies and participating mass ratios. It's okay. And you can see the tables by switching this from here. So you have mode 1 to mode 12. And the periods look fine. Let's go for model participating mass ratios, and the cumulative sum of masses of each modes in X and Y should be 90% and above. You can see from the number of modes considered. So we can see 12th mode, it's already 100%. It's about 6th mode, you can see 93 and 95%. So you don't have to increase number of modes. This model results can be used for the spectrum. Now you can continue with the results, or else you'll have to unlock the model and work on the mode shapes and update the model results to the acceptable level before reviewing these spectrum cases. So under the display, you have joint outputs, the support reactions, joint reactions. You can get the values like this. You go to the force stress diagrams. Axial load or value with values. And if specifically if you go for spectrum results, you'll see all are positive values. That's the nature of the analysis. You'll get absolute maximum value. To deal with. So program is capable, both ETABS and SAP2000 both are capable of dealing with these spectrum results in the design. So it will create 8 sub combinations, changing the signs, permutations. For example, for a column there will be P, M, and M2 and M3 biaxial moments. So the signs will be changed of 8 permutations, and then the maximum obtained from that will be used in the design. So that is something taken care in the design automatically by the program. So, but how to perform a response spectrum analysis, this is how we do in the program. This is applicable to ETABS as well. So this one example I wanted to show you covering all these features. These are whatever definitions and other definitions we made, right? It's same for any model, any structure that you're going to create here. Now let's move to some advanced analysis. And let me start with a pushover analysis. So I'm going to create a new model for that. Let me use a 2D frame quickly, a simple portal, number of stories, let's say 5, number of pages, keep 1, 6. I'm leaving it to the program. We will review the section properties quickly after this. Can see this. Let me save this. By default, section property fsec1 has been created by the program. If you look at it, it is a steel section of FE345. So this example is only to demonstrate you how to define and model and also analyze a pushover analysis, particularly floor analysis case. So it's about 300 mm on feet or 300 mm I section, right? If you wish, if you want to change the properties, you can import new property steel section, and it will take you to the install location. There will be a under SAP2000 property libraries. Under that, you will have sections of various regions or country-based XML files. In that, you can select, for example, Indian, and use and set the material and select, let's say, ISMB 300, and then import it. It will be added to the list. And if you want to assign this, you can go to the assign, select the member, and select the property and assign it. That's how you change the property. All right, that's how you import library sections. Now for the pushover analysis, I'm going to quickly add the frame loads. Dead loads, say 10, say 20. Display show on deform shape will clear all the display of assigns, or you can also clear it from assign clear display of assigns. So for the pushover analysis, we are interested in studying the moment plastic rotations happening in the frames due to the uh, lateral displacement of the structure. And for that, we'll have to assign hinges to study. So plasticity is everywhere on the structure, but based on the previous experiences, and we know the failure modes of frames and other buildings. So, and specifically for the member level, we have the ends of the beams and ends of the columns, frame members will yield or enter into the plastic rotation, that state. So we assign hinges at those locations. So program allows you to assign hinges at desired locations, but we'll be assigning only at here. We also need to keep in mind that the computational efforts that you'll have to make if you assign so many hinges. in your model. But again, it all depends on the problem that we are trying to solve here, right? Let me start with the loads I have assigned. Let me assign with joint restraint fixed. And then we have the definition to make. Under section properties, we have hinge properties. We want to define hinges manually like this of various hinge types, force control or deformation controlled, and moment hinges or interacting PM to M3 for columns, right? Shear hinges, axial hinges for braces, etc. all are available. Yeah. You also get fiber hinges. Program also gives you option to assign hinges. So that's the definition we'll make in case of any user defined. Here, I'm going to assign hinges, auto hinges I'm going to use. So based on, you can see there is an option called auto. When it is auto, you can assign hinges based on ASCE 41 code. Based on American standard. Earlier, we had the FEMA and ATC. Now we have the code ASCE 41. Based on that, there are standard hinge definitions we can make use of. This is for steel beam. So I'm going to use this steel beams and M3 hinge. The major moment bending about with local 3 axis. I'm going to use M3. So nonlinear beam hinges. You can see. I'm going to assign to these frames. So you apply this, we close this. So we have assigned auto M3 hinges. Next, let's assign for columns. But this time it would be for steel columns. And it will be for axial and M3. So I'm going to push the structure laterally in X direction. This is the XZ plane. So in this direction, we're going to push. And for that, the orientation of this column will be like this. 1 is along the height, 2 is in this X direction, and 3 is in Y direction. So rotation will be about 3 or the about Y. So P M3, or you can also use M2 or M3 using this particular hinge. So program can update the hinge information. Then if you go back to section properties and look at the hinge properties and enable show generated props. And now you'll be able to see the assigned hinges automatically generated by the program. So one H1 and one H2 at the base and at the top. So it's a column hinge. Let's go to the modify show. Oh, sorry, this is 11. Right, this is for the beams. So this is a beam hinge, 11 H1. And if you go there, and here you can see the definition. Similarly for the column 1H1, so ratio is interacting PM3. You can also convert into user defined and modify the values accordingly. So you have all the features one would expect, right? Our focus would be on the modeling and the other definitions that you make for the pushover case. Next, you can define a load pattern to apply the loads. It can be uniformly distributed in all stories, or you can also use automatic auto lateral load type. For example, a quadratic distribution, triangular distribution, right? And you can use that pattern to apply the lateral push for the pushover analysis. You can also select acceleration load also. That is also fine. For that, I will enable the mass source from the applied loads. So you can define such pattern, or you can directly go and assign using the option available inside the nonlinear static case. So now we are going to define two cases. One is load case, add new load case. We call it as gravity, and it would be static nonlinear. The load pattern is dead. All the dead and other loads in the gravity direction are defined here. Is applied in a full state. Final results you'll get. It starts at zero initial condition, and we will use this as a starting vector for the pushover case. Now add new case. This is called POA, or you can call it as push X, so that you can say this is in push in X direction. So it is a static non-linear and continue from the state at the end of gravity. And then here you can specify the load type, if you load pattern, acceleration, or mode. You will use acceleration, UX. Let scale factor be 1 for now. Also use 9.81 because and importantly, we would like to see the results in multiple states. So load application, first of all, as a displacement control. So we are going to specify, let's say 0.3 monitor displacement of 0.3 or 300 mm, and U1 is the X direction joint translation displacement that we are going to see, and the joint at 6. This, and then to this we'll also tell the program save the results in multiple states. Minimum is 10, maximum is 100. So nonlinear parameters for the analysis can be controlled or specified here, accepting the defaults. So this is the definition that you'll make for the pushover case. So joint label is 6. You can right click and find the label, or bring in the Z display options to see all the labels in a graphical window, and you can use it. So I'm selecting this particular joint to monitor the displacement. So now we can run the analysis. And whenever you're doing a portal frame analysis, something which is in a 2D plane, you can also set the analysis option and set it as or only those degrees of freedom available to the analysis. This should be okay for XZ plane, and we can start the analysis. Once analysis is complete, you can go to the display and check various outputs. You can see the show pushover curve. You can see pushover curve. It's a negative. You can change the sign so that it can be on the positive side. That's okay. You can also switch the plot type like ATC40. You can see the performance point captured, ADRS spectrum, and you can have PMA 356 coefficient, equivalent linearization, and nonlinear static procedure. You can also bring in your response spectrum curves using modify show parameters and specify, modify these values and get the output and perform basically the performance based design concept. The required data are available here already, and you can modify the input parameters, tweak them, and get the output in various formats. Right. So I'm quickly stopping this particular output, and then you have the hinges now. Let us start with the show deform shape and specifically the pushover case. Step one, apply. You close this, and you can see the scale with colors. So step one, it's about 30 mm. So no hinge formation, and there is a arrow button, toggle buttons next to start animation when it is displaying the deform shape. You can use next. Step two, step three, and you can see hinge formation is just yielded. It is in green color. 5 more hinges are forming. The displacement about 140 mm. 6, 7, 8, and you can see the change in color as well. For 218 mm, 9, 10. Last step, about close to 300 mm. This is how the hinges are formed. Select any column member or beam member. You can select and go to the display, and there is an option called show hinge results, and you can see uh, show backbone, and you can for moment or axial load. You can see basically the hinge response. It is lost from here. Step 8, and then similarly, if we check a beam, I think beams just yielded. It just yielded, so we can see that green dot here. Can get, I think, the tables. State and status. State is about the backbone curve, and status is about the acceptance criteria such as immediate occupancy, life safety, and collapse prevention (CP). Both are displayed here. These are available here in this definition: immediate IOLS and CP definitions, and ABCD are here the control parameters for the backbone curve definition. Right. This is one particular example on pushover analysis. One important another example is performing time history analysis, and you'll use the same model. So I'm going to do a save as of this model and remove unnecessary definitions from there. So I'll use So in this example, I'm going to show you how to model a link, which is going to act as a base isolation device for this superstructure to model and assign at the base and apply it with a real-time earthquake data and how to perform a time history analysis. So all three combined here. So let's start with the definitions, section properties, and under the link, add new link property. And you have various types like multilinear elastic, multilinear plastic, dampers of specific types, exponential bilinear friction, gap hook elements, plastic, standard plastic when model for defining FT, and then you have rubber isolator, and then other isolator types, friction, triple pendulum, etc. A wide range of definitions are predefined or types are available. I'll use rubber isolator for this example. So typically, we are interested in the lateral displacement of these isolators, the rubber isolators. So U1 is vertical, U2 is lateral in X direction as default, U3 is in Y direction. So we are dealing with XZ plane, so I'll use only U2. And in the vertical direction, I assume it is highly incompressible, so I'll fix this so that there will be no vertical settlements. We are interested in the nonlinear behavior of this deformation behavior definition. So for linear analysis, I'll provide effective stiffness of 1000, and then for the nonlinear to provide stiffness of 500 and yield strength as 10 kilonewton for post yield stiffness ratio 0.1. So the definition about this particular type can be obtained from the help under the help document, manuals, analysis reference manual, CSI analysis reference manual. In that, explain these definitions are explained in detail. You can also always refer to that, or for all the other types as well. So don't worry about these values that I'm providing here. It's just for presentation. Then link has been defined. Now to model this, I'm going to create a space to accommodate these links. And draw two joint link. The link we just defined, and then for drawing this, let me create two joints there. Edit, select these and use replicate to create. I'm going to draw the link for 300 mm. So I'm going to create a joint there, the Z direction. And now we go to draw two joint link. You can also model it as one joint link, but two joint will be more easier to visualize. That's why I'm using this draw. And then under the draw, there is a reshape element. I'm going to reshape this column and place this at the top of the link. This one, the top of the link. I'll remove these, the fixed restraints attached to this. I hope you can see this. The link, bottom fixed, and the link top is connected to the superstructure column. All right. And then I don't want to study the nonlinear behavior of the superstructure, so I will remove the hinges previously defined, none, and apply. Nonlinear hinges, none. Right. We are interested in only in the isolator level where the nonlinear behavior is expected to happen. Superstructure remains elastic, a concept that we consider in superstructure isolation. However, you can assign and study the nonlinear analysis as well. Let's go to load functions. Sorry, define functions. There is an option called time history. Under the time history, you can import from file. Other standard cosine and sine functions are also available. We'll use from file, add new function, and the real-time earthquake data you can obtain from various sources over the internet. Um, for the demonstration purpose, I'm going to use a sample earthquake data available in the install folder location. So I'll use browse. Under the install folder location, you can find time history functions that there are few sets of data are available. So for demonstration purpose, I'll use only one time history, Altadena. So formats will be different from different sources. So you'll have to tell the program how to read the file properly and view the file, and you can see how the format is. So this for this file is like 2 lines of information that gives Altadena the station, and then the angle 0 degree and 2000 points of acceleration data. So acceleration time history spaced at 0.02 seconds. Units is centimeter per second square, right? And then you have the actual data from the third line, and each line is carrying 8 data. Likewise, you have 2000 points. So this, do not save this. So you have to tell the program skip lines, 2 lines, no prefix characters to the data, and then number of points per line 8, and then values at interval of 0.02 seconds, and then display graph. And now you can see the at an earthquake approximately about 40 seconds. Altadena, then press OK, is added. Likewise, you can have multiple definitions. Now define a load case. You will delete the pushover case, and then we'll add a new load case, PHA X, so time history analysis in X direction. So load case type, this time we'll select time history. Analysis type is nonlinear. Solution type can be based on model or direct integration. You can choose. Let's go with the model. And you specify acceleration as a load. U1 is X direction. Altadena is the function. And scale factor, you need to match the scale factor between the file, input file, and the model. Model is in meters, so it is centimeter. So you need to multiply it by 0.01 to convert it into meters. So that's the load. And number of output time steps. The time step is 0.02 as per the input file. So we have 40 seconds. About we'll go up to 20 seconds where there is no more excitation, and to divide it by 0.02. So you'll get 1000 output, number of output time steps. That's 1000. So that would be for 20 seconds. And model damping, you can specify constant damping for superstructure is 0.05. And the first mode will be isolator mode. Those who are dealing with isolator uh, in your projects, they will know isolator mode will be higher, and then the damping value will be based on the design of the isolator. The manufacturer of the device will give you those information. So let's assume approximately 15%, 0.15 for the first mode. It's an override, and then rest of the modes will have 5% of critical damping for all other modes. It is based on a model. So we're going with this, and so program is capable of doing both model time history analysis as well as direct integration like numeric beta, Wilson theta method, etc. using step-by-step integration, direct integration. Let's go with this and let's run the analysis. Don't need the gravity for now. Let's go with. So the analysis is complete. This is okay. You can see the first mode, t equal to 2.0. So shifted the time period, which would be typically around for this kind of high-story building to about 0.5 seconds, something. They shifted it to 2 seconds. That's what we do with the base isolation. Reduce the superstructure. Excitation. Right now, after the analysis, you get to see the display. So it is a history. So you'll have to see the show plot functions as a response history. So you'll go to the plot function, and for the time history case, we'll define plot functions. For example, the roof level, acceleration. Let's say joint number 6, the top joint, and we will see absolute acceleration of this in UX direction. We'll modify the function, name it as ABS ACC, acceleration, right? And you can add the function. Likewise, you can define a number of plot functions and use it here to plot them, right? I'm going to plot this. This is acceleration versus time plot. And you can see this response of that particular. You can also add the input function. Load functions, I mean, acceleration in one. You can add both and see both. So the acceleration at the base, you can see in green, larger values, and then the due to the isolation, the orange color. We can extract it to an Excel using the output here table, and then plot this in a detailed presentable format. And you can see the response there. So it has reduced the acceleration, right? So one more is the link forces, basically the deformation of the link in U2, and then add one more link 1 I and J and force, shear 2, the shearing displacement. link 1, this is F, force, link 1, this is D, this is deformation. Can remove this and add force in y-axis, vertical function, and the horizontal plot function will be displacement. And you can see the force deformation response for this particular case of the link element. Right. So these are the examples I wanted to cover. There are other examples you can also explore on your own. If you have any queries, then please let us know. So tomorrow is also we have the CSA bridge